Hey everyone, welcome to Tutoring. Hope you're having a great day. Today we are doing a tutorial video on chapter 7b. We'll be doing question 1J and question 2I and J. So this is your integration using or involving inverse circular functions. So before you get baited, it's not the anti-deriving inverse circular functions. It's anti-deriving functions such as these, which might look familiar, and then you get inverse circular functions as your answer. So let's go into the question. J, we'll do 1J first, and then we'll do the 2I's and 2J. Okay, so in 1J, if you look at your function right here, what does that look like? If I was to derive an inverse circular function, which one does that look like? Well, it doesn't have a square root, right? So no square root means there's only one function when you derive, doesn't give you a square root in terms of this inverse circular functions, and that's the tan inverse. If I derive tan inverse of a, x on a, I get a over a squared plus x squared, right? So in that case, guys, this looks very similar. I'm just going to replace x and y. It's the same thing really, but you have your a squared, you have your x squared, your y squared, and then your a. The only problem is the a. The a does not look the same. So I'm just going to write it in a format so that you can actually visualize and see what's happening here. So you can take the 7 out because as we all know, you can take numbers out and you have 1 over 3 plus y squared, anti-derived in terms of y. Now, the reason why I took 7 out is so that we can play around with this function here, okay? So 7, just leave it out, that's fine. It's not a, it serves no purpose. We just take it out. But now, this number 1 is still not a. If 3 is a square, then a should be root 3. So my goal is I want to turn that 1 into a root 3, right? If I have this function right here, then we know clearly that if we anti-derive this, we get tan inverse of x on a is our root 3. So we get tan inverse of x on root 3. But we didn't have a root 3 to begin with. Of course, here's the magic, guys. You can just bring the root 3 in. That's fine, it's just a number, right? But if you want to bring a random root 3 in, you have to divide it by root 3 as well. So that root 3 and root 3 never exists to start with. And that's why we divide. So yeah, bring it in root 3, but make sure you divide it as well because they shouldn't exist in the first place. And there we go, guys. You have 7 on root 3. If you anti-derive this, right here, you should get tan inverse of y on root 3, okay? And then plus c. Expand this and you get your answer. And that's how you do 1J. It's just an indefinite integral. Just you have to take advantage of the fact that your 7 is a number. You can just take it out and then you can replace things, okay? So that to make it in, so that's in this format where you can anti-derive to get your tan inverse. So that's 1J, guys. Let's move on to the next one, 2J, okay? So once again, if you see this format, there's no square root at all. The only function that comes to mind in terms of inverse circular function is the tan inverse. If I derive tan inverse of x on a, I get a over a squared plus x squared. Now what's the problem here? My x squared has a coefficient that is not 1. This is 3. So what you do first is you want to take the 3 out, okay? So what we do is I'm going to write the integrand again. I'm going to take the 3 out. So it's 1 over 3 actually, plus x squared, anti-derive in terms of x. I take the 3 out and we're left with 2, 0, 1 on 3 plus x squared dx. Okay, now my integrand, once again, we're going to use the same thing as what we did with j. My a squared is now 1 on 3. So what should my a be? So if a squared is 1 on 3, if you want to find just a by itself, you square root that. So you want your number on top to be square root of 1 on 3, which is 1 on root 3. And then you have 1 on 3 plus x squared dx. Now the 1 on root 3 never existed to begin with. You have to turn it back into a 1, right? So how do you turn 1 on root 3 back into a 1? You times it by root 3. And we had a 1 on 3 here, so it's just 1 on 3 times root 3. But this root 3 and that 1 on root 3 cancels each other out, which is what we want, okay? That 1 on root 3 never existed. We only made new numbers so that we can anti-derive this and get our tan inverse, which is over here. And then there we go, guys. It's root 3 on 3. Anti-derive this, we get tan inverse of x on a. X on a is x on 1 on root 3. X on 1 on root 3 is root 3 times by x. And then you sub in your numbers, 2 zeros. And there we go. If you want to find your answer, guys, it's root 3 on 3, tan inverse of 2 root 3, and then minus tan inverse of 0 when I sub in 0, Well, tan inverse of 0 is 0 because that's sine inverse divided by cos inverse of 0. Sine inverse of 0 is 0, and then of course you just get 0. Okay, tan inverse of 2 root 3, unfortunately, there is no way to solve for it, so your final answer is root 3 on 3, tan inverse of 2 root 3. Okay, so that's pretty much 2j, guys. Let's move on to the last one, so something that's not tan inverse. So as you can see in this function right here, your integrand, now there's a square root. If there's a square root, well, the only thing that comes to mind is your sine inverse and cos inverse, right? And preferably, yeah, you can use any one of them. I like to use sine inverse because I don't have to deal with the negative sign. So sine inverse x on a, that is equals to 1 on square root a square minus x squared. Okay, so if I derive sine inverse, this is what I get. My format looks very similar. See, that's the a, kind of like the a squared minus like the x squared, right? But the problem is the coefficient once again is a 9, that's not a 1. So what you want to do first is you want to get rid of the 9. So take the 9 outside. So square root, I'm going to take the 9, factorize it out. 1 divided by 9 is 1 on 9, and then you have the y squared, the antiderivative in terms of y. The square root of 9 is square root of 3, and there we go. 1 on 3 is 0. I'm going to take the 3 out as well, and if you take the 9 out, it's 3, so it's 3. So it's 3 divided by 3, which is good. 1 over square root 1 over 9 minus y squared dy, and we're almost there, guys. 3 divided by 3 is 1, perfect, cancels out, and your final form is 1 over square root of 1 over 9 minus y squared dy. And the good thing about sine inverse compared to tan inverse is the number on top is 1, okay? It's not a, it's just 1, so you don't have to change anything. You don't have to make any new numbers. You already have your format here. So we can actually go straight into the antiderivative, which we get sine inverse of y on a, right? So what is a? A is the square root of 1 on 9, because 1 on 9 is the a square right here, see? That's the a square. But we want to find the square root of that, which is 1 on 3. So it's y over 1 on 3, and that's a sine inverse, and then we sub in 1 on 3 and 0. Okay, I'm going to write it neatly here. It's sine inverse of 3y, because y over 1 on 3, I just bring 3 up top, 1 on 3 is 0, and we can definitely solve for this. What is sine inverse of 3 times 1 on 3? That is sine inverse of 1 minus sine inverse of 3 times 0, that's sine inverse of 0. And then sine inverse of 1, that is pi on 2. So if you have to take a look here, sine inverse is when the vertical position is 1. And the only way for that to be positive 1 is up here, which is pi on 2. And then sine inverse of 0, where is sine pretty much 0, and that's 0, okay? So it can be pi as well, but as you know, the range of sine inverse is negative pi on 2 to pi on 2, so you can only take 0. So it's pi on 2 minus 0. Final answer is pi on 2. So that's pretty much it for this chapter, guys. Hopefully you found this video useful. If you did, leave a like and maybe comment any questions that you are still doubtful about. But aside from that, guys, thank you for watching, and I'll see you in the next video.